Good morning and welcome to Computer Science 221. We're beginning a new chapter today. I know you find that all very exciting. Chapter 3. Chapter 3. Let me come over here and fix my pen. And we're going to start building circuits. Lots of interesting things to talk about. Before we go on to anything, this chapter, first of all, the first section of the chapter, 3.1, some very technical discussion about transistors, which you can read over very quickly, and if you find it exceedingly confusing, you shouldn't worry because it really has nothing to do with the rest of the book or the rest of this class. If you're an electrical engineer, you would find it very interesting. But otherwise, it really doesn't apply to us at all. But after that very technical talk about transistors, there is something that your author talks about called DeMorgan's law. DeMorgan's law, or some people refer to it as DeMorgan's rule. And it's a very simple rule. It has to do with negations. And basically, if I have an expression that looks like the following, A and B, and I want to negate the whole thing, I come over there and I'm going to say not A or B. Is there an alternative way of writing this? And it turns out that there is, and this is going to be very useful for us. What we can do is we can think of it this way. We can distribute the not over the A and B, and the and is going to become an or. So this looks like the following. This would be not A or not B. And the other form of this rule looks like the following. If I were to say not A and B, the same thing, I'm going to apply the not over the A and B, but whoops, I made a mistake here. This should be an or. So this is an or. Okay, so this is going to be not A and not B. Now, we should prove this, okay? If I come over here and I have A and B, and then I would have A and B, and then I would have not A and B. Let's make a truth table here and see what that looks like. Okay, now for and, the only time this is true is in this situation down here. And now over here, if I'm going to invert this column, I would get 1, 1, 1, 0. Now if I extend this table a little bit, okay, so what we're trying to prove is that not A and B, I'm going to come over here, and I'm going to say not A. I'm going to come over here and I'm going to say not B. And then over here, I am going to have not A or not B. So if I'm going to have not A over here, I'm going to take this column here and completely invert it. So this would be 1, 1, 0, 0. Not B, I'm going to invert this column over here. So that's going to be 1, 0, 1, 0. And now what I have to do is I have to OR these together. So remember, OR is going to be true anytime either side is true. So this is going to be true, and this is going to be true, and this is going to be true, and this is going to be false. And the thing to note is that this column over here and this column over here look exactly the same. So what we've done is we have proved that one right there. Now I'll leave it as an exercise for you to go through the same table, same similar table, to prove it for this one over here. It's not a difficult exercise, and I'm sure that you're going to have a lot of fun doing that. Now, we've talked about lots of different gates up till now. We've talked about an AND gate, which would look like this. And we've talked about an OR gate, which would look like this. And we've talked about a NOT gate, which just has one input. Looks like that. And now we also have this thing that's called a NAND gate. And that's going to look like an AND gate. But then what happens is we take the output of it and we invert it. And this is, we don't usually write it this way. The way that we usually write it is like this. We put a little circle there, and the circle indicates that we're inverting the signal. Likewise, we have something called a NOR gate. And what an OR gate is going to look like is it's going to look like an OR gate, but we're going to invert what comes out. And it looks like that. Okay? Now, I want you to remember when we were designing circuits. For example, one of the circuits we designed, and you'll see it in this chapter, but I believe it was also in the last video that I made, we had something called a full adder. And when we did the full adder, we had A, and we had B, and we had something called the carry in. And then we had the sum, and we had something called the carry out. And the truth table looked something like this. And again, the sum here would be 0, the carry is 0, here the sum is 1, the carry is 0, the sum is 1, the carry is 0, here the sum is 0 and the carry is 1, here the sum is 1, 0, over here we have a sum is 0 and a carry of 1, a sum of 0 and a carry of 1, and over here we have a sum of 1 and a carry of 1. Now these are two different circuits. We have the sum circuit and we have the carry out circuit. But what happens here is that if I wanted to say build the sum circuit, what I do is I have to come over here and look at the rows where the sum is 1. So there's a row like that, and there's a row there, and there is a row there, and there is a row down here. And basically what we're saying is the sum is 1 when I have not A and not B and C in, or I have not A and B and not C, or, so the idea that I'm trying to get to you is that each one of these conditions right here, these are ANDed, but then what I do is I OR them all together. Okay, so that in fact I could write this as a function. I could say that the sum is equal to not A and not B and Cn, okay, or over here I would have not A. Whoops. Watch what I'm writing and what I'm saying. This should be not A. And B and, let's see, this would be not C in, or, and you can see how this pattern's going on. But the point that I'm trying to make is that I have a bunch of AND gates, okay, that have these three inputs. So they're going to be a bunch of AND gates. And what happens is that these are all going to come into an OR gate. And what's going to happen is we can see that some of the inputs to these things are going to be inverted. So there might be an inverter over here somewhere. There might be an inverter over here somewhere. Okay? But the point is that I can construct any Boolean circuit I want with AND gates, OR gates, and NOT gates. Now, it turns out to be an extremely powerful result that both NAND gates and NOR gates are what are called universal gates. And what that means is that I can build any Boolean circuit I want just using NAND gates, or I can build any Boolean circuit I want just using NOR gates. Now I need to prove that. So to prove that NAND is universal, we must show we can implement AND, OR, and NOT with just NAND gates. Well, watch. If I come over here, if I have A, and then I go A and A, and then I come over here and I go A NAND A, watch this. This is pretty simple. If A is 0, well then 0 and 0 is 0. But then not 0 and 0 would be 1. And if A is 1, then A and A is 1. And then A NAND A is going to be the not of that 1 is going to be 0. So you can see that A NAND A turns a 0 to a 1 and a 1 to a 0. This is equivalent to not A. Okay, so we have taken care of this one over here. Now, what happens if I have A and B, and I go A NAND A, NAND B NAND B. Now, this is going to be interesting, so watch closely. 0, 0, 0, 1, 1, 0, 1, 1. Well, first of all, we know that if A is 0, A NAND A is going to be 1. So I'm going 1 NAND, and if there's a 0 here, there's going to be a 1. Well, I know 1 and 1 would be 1, so not that is going to be 0. Okay? Okay, if I come over here and I have a 0, A NAND A is going to be 1, so this is going to be 1 NAND 0. Okay, well, I know that 1 and 0 is going to be 0, so if I invert that, that's going to be a 1. I come over here, and if I put a 1 in here, this is going to be a 0 NAND, and if I put a 0 in here, that's a 1. Well, I know 0 and 1 is going to be 0, and if I invert that, that's going to be a 1. And if I come over here and I go 1, if I put in a 1 for A, that's going to be a 0 here. That's going to be NAND 0. Okay, well, 0 and 0 is going to be 0, and if I invert it, it's a 1. So I get that. So when I go A NAND A, NAND, B NAND B, I get this column right here. Well, notice this column right here, this is just A or B. So now I have shown I can implement OR just using NAND gates, and I just have one more to go. What I'm going to do here is I'm going to have A, B, and I am going to have A NAND B NAND A NAND B. Okay, now let's think about this one. Zero, 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 1, 1, 0, 1, 1. Well, if I put a 0 in here, A NAND B, 0 NAND 0. Well, 0 and 0 would be 0, so if I NAND it, it's a 1. And what's nice about this is if this is a 1, this is a 1. And if I NAND those together, I'm going to come over here and get a 0. If I come over here and I go 0 NAND 1, well, 0 and 1 is going to be 0, and if I NAND it, it's a 1. And I'm going to get NAND, and this would also be a 1, and that's going to give me, so 1 and 1 would be 1. If I NAND it, that's a 0. If I come over here and I go 1 NAND 0, well, 1 and 0 is going to be a 0, so if I NAND it, negate it, it's a 1 NAND 1, and again, that's a 0. And if I come over here and I go 1 NAND 1, okay, well, remember 1 and 1 would be 1, so if I negate it, it's a 0, and I get NAND 0, and we know if I AND 2 zeros, I get a 0, and if I negate it, it's a 1. Well, look at what I have here. That's just A and B. And now I've done all three. The conclusion, okay, NAND is universal. And for homework, I say do the same. For NOR.